All right. So there was a question on my other login, but going over question 40 just to make sure that we're clear. So let's talk really quickly about question 40. So question 40 is saying if x is not equal to y, set z equal to z plus 1. Well, that's similar to saying if x minus y is not equal to 0, set z equal to z plus 1. So same idea, move y into the W register, subtract the W register from file register X, so that's y subtracted from X, put the result back in W so we don't change X, and then we could say branch of 0 to a label I'll call don't increment. So if x minus y is 0, I do not want to increment. Otherwise, I want to increment file register Z, and then my don't increment is a label down here, and I would just continue with my code at that point. So something like that would code it up fine. The other thing you could do at this point is you could say branch if not 0 to do the increment. Otherwise, branch to skip the increment. And then do the increment would be a label where I would say increment file register Z. And then skip the increment would be after that. So what's the flow here, right? Calculate y minus x. If it's not 0, I'm going to jump down here and increment z, and then end up here. If it is 0, I'm not going to do this branch. I'm going to jump to skip the increment, and I'm going to end up here without incrementing z. So in either case, this is what gets accomplished. Alright, so I will post homework on Canvas after class, but I would like you to work on questions 49, questions 41 and 42, which use skip instructions. So we have to talk about skip instructions next. 49 through 52, which we will talk about what I want you to draw when I ask you to show the stack or draw an abstract stack. So we'll go through examples of that. And then 53 through 57, which we will start talking about today, but we'll probably finish up on Tuesday. So we may not get through everything that you need to do these questions, okay? But that's what we're going to work on later on today and definitely on Tuesday. All right, so let me talk about stacks first of all, because we were doing stacks last time. Let me finish this up, this idea of drawing a stack. So we talked about the stack inside the PIC processor, but it's really an example of something very general, this idea of a last in, first out memory. And so, you know, I described the pile of dishes at the salad bar, and when you put a dish on the top, right, all the other dishes push down, and now the top of the stack is that last plate that got put on. And if you pull that plate off, you remove the top of the stack, and the dish that was below that moves up to the top. And so we can imagine a pair of operations like push and pop. And so we might push, let's push a dog, and let's push a cat, and let's push a bunny. And I'm using silly arguments because this is not PIC processor code. Okay, the push instruction on the PIC does not take an argument. It just pushes the program counter where the next instruction is stored in memory. So this is an abstract notion of a stack. Okay, this is not something we would write in PIC assembly language. But I want to show you how you can draw a stack. So normally, you know, if we start off with an empty stack and we push a dog on top, well, there's a dog sitting on top of the stack. And now if we try to push a cat on top of the dog, what happens? Well, the dog moves down one level and the cat goes up on top. And now if we try to push a bunny on top of the stack, the cat moves down one level, the dog moves down one level, and the bunny comes out at the top of the stack. So this is the top of the stack, TOS, and we've got three things. And this is the bottom of the stack. Okay? PIC processors don't have erasers inside. So we need a different way to manage a stack instead of moving things up and down the way we would with a spring-loaded pile of dishes. So here's what we do. We draw our stack something like this, and we allow the top of the stack to move in this chunk of memory. So normally top of stack points at this first entry. So when we push a dog, what we do is we put a dog in the next spot and we change top of stack to point to that. And then if we push a cat, we put a cat here and we change top of stack to point to cat. And then if we push a bunny, we change the top of stack to be here where the bunny is. And if we index these from 0 through 31, we can have a stack pointer. So it's usually just called SP for stack pointer, but on the PIC processor it's called STKPTR. STKPTR points to the top of the stack, the last thing that was pushed on the stack. And the advantage of this is when I push something new on the stack, if I decide to push an elephant, I don't have to move the things that are already on the stack. I simply increase the stack pointer and I put my piece of data that I'm pushing into that new location. So now if I want to know what's at the top of the stack, I look at my stack pointer. Stack pointer is equal to 4, so whatever is at location 4, that's the top of the stack. And now if you say pop, how do we pop the top of the stack off? All you have to do is decrement the stack pointer. Change your stack pointer to point to element 3, which is the bunny. So yeah, stack pointer automatically points to the newest thing on the stack. And you may have noticed that even though I popped off the elephant is still in the stack. Right? Security alert. That's a potential exposure. When you pop things off a stack, they don't usually get removed from the stack. It depends on the architecture of the machine. But in a pure stack, removing something from the stack doesn't actually remove it from the memory. It changes the stack pointer and says this is no longer part of the stack. This is the top of the stack. And so cat's on there and dog's on there also. But the elephant's still kicking around in memory. And if that elephant has, secure information, somebody else could access that. Not a problem on the PIC processor. Alright, so if you have a homework question which says something like this, draw the stack following these operations, push 50, push 80, pop, push 90. Right, what would you want to draw? Well, I would start off with a picture of my stack. And I would say the stack pointer points right here, or maybe top of stack. Which one do I ask you for? Show the stack pointer and top of stack registers. Okay, so for an abstract stack, right, I would start off with this. So that's my initial stack. After I say push 50, my stack would look like this. It would have a 50, and my stack pointer would be pointing right there. After a push of 80, my stack would look like this. After a pop, my stack would look like this. And after a push of 90, my stack would look like this. Right? The stack pointer moved back to the 50 here because I popped off the 80, which means that if I want to push, I'm going to push that 90 in the location after the current stack pointer. So I'm going to increment the stack pointer to this cell down here, and I'm going to write a 90 in there. Okay, this is all there is to stacks, but there's a lot of nuance, lots of little ways you can get this not quite right. But basically, the way we're picturing stacks, stack pointer shows you the last thing that was pushed. And if I had a top of stack register, my initial top of stack, who knows, because my stack is empty. After I push a 50, top of stack is equal to 50, right? The contents of the thing at the stack pointer. After I push an 80, top of stack is equal to 80. After I do my pop, top of stack is equal to 50. And after I push a 90, top of stack is equal to 90. Alright, so that's what's going on with this chunk of questions from 49 through 52. 49, you're doing an abstract stack. Okay, so just draw me the pictures of doing 2 pushes, a pop, a third push, and 3 pops. So 6 pictures. Okay. Question 50 is just kind of looking up in the data sheet, right? Show me a picture of the stack. So figure out how big the stack is, figure out what the initial values of stack pointer and top of stack are. Right? You can find those in table 5-2. And then 51, 52, you're actually hand assembling some code, right? And every time that you call or return, you're working with the stack. So when you call sub, you want to push the address of the next instruction. And I'll give you a hint. Origin 80 says that this call is at location 80 in memory. What's the address of the next instruction in memory after that call? It's going to be 84. In my program that I'm writing, my next instruction is an increment which is at location 100. But that has nothing to do with what happens when the processor is running binary machine code. Origin 80 says the call is going to be stored at location 80 in program memory. When you say call, the address of the next instruction in program memory gets pushed onto the stack. Call takes 4 bytes, call is at 80, the next instruction is 84. 84 gets pushed onto the stack. Okay, not 100. And when you return, you pop off the top of the stack and you go there. So draw pictures of the stack pointer, and the top of stack register, and show me what they are after each of these instructions gets executed. And you have 3 instructions. You have a call to sub, you have an increment, and you have a return. So 3 pictures. And then same thing down here, but you have 4 instructions: an increment, a push, and a pop. And remember, push pushes the address of the next instruction in memory. Pop just pops off the top of the stack and doesn't do anything with it. Alright, let's talk about skip instructions. I don't like skip instructions in most cases. As I said a few weeks ago, most people get skips wrong. Okay? But there's one case where skip instructions are really useful, which is for testing individual bits. But maybe not. But let me show you what skips are, because you'll learn about them on the street eventually anyway. So go back to your data sheet, and let's go back to table 20-1. And down here with these conditional branches, sorry, not byte-oriented instructions. There are these instructions: compare file and skip if equal, compare file and skip if greater, skip if less, decrement file and skip if 0, skip if not 0, increment file and skip if 0 or not 0. And there's some bit instructions: bit test file and skip if clear, bit test file and skip if set. Okay, here's what a skip instruction does. It gives you the option of skipping one instruction in your program. So for example, I can say, well, let's go MPLab. No, let's not go MPLab. Let's just talk about this. Let's say I say increment file and skip if 0 hex 80. Okay, this is going to do two things. It's going to increment the contents of location 80 no matter what. It's always going to increment this file register. So it's kind of like just an increment file register. But the SZ does one extra thing. It says, after I've incremented, let's see if the result was 0. And if it is, don't do whatever this next instruction is. Go on to the instruction after it. But if when you increment this register the result is not 0, just treat it like a plain old increment. Right? Increment that, go ahead, do the instruction after, do the instruction after that, and so on. And so here's a really standard loop that uses skip instructions. So move LW 9, move WF into some file register like count. Here's a loop. Decrement file and skip if 0 count, branch to loop. Alright, we put a 9 into this file register count, we decrement it, and if the result was not 0, it will not skip this next instruction, it will do the branch back up to loop. So count goes to 8, skip if it's 0, well it's not 0, so it's going to do the branch. Decrement it again, it's going to be 7, 7 is not 0, it's not going to skip. But if count is equal to 1, and we say decrement file and skip if 0, count will get decremented to 0, and since 0 is 0, it will skip this next instruction, which is a branch, and will do whatever is down here, whatever this next instruction is. Okay, this is the same thing as this. Decrement file count, branch if 0 skip, here's your next instruction, and then here's skip. So decrement your file, and if the result is 0, skip over one instruction. Okay, that's what this does. And there's decrement file and skip if 0. There's decrement file and skip if not 0. There's a pair of increments that do the same thing. Increment file and skip if 0 or not 0. There's compare files, which lets you compare a file register to the W register and skip if they are equal, if F is bigger than the W register, or if F is less than the W register. There's also test file and skip if 0, which checks to see if a file register is equal to 0, and if it is, it will skip the next instruction. These are slightly more efficient than doing conditional branches. Right? They code more efficiently, they keep the pipeline full, but they're so confusing to most people that I prefer you just kind of avoid them, except for the occasional 2 homework questions that you got this week. But the bit test files are useful sometimes. Bit test file and skip if clear, skip if set. So we can check a single bit in a register and say if that bit is set, skip the next instruction. Or we can say if that bit is clear, skip the next instruction. Clear meaning 0, set meaning 1. You don't need to use these, right? I could take my register, I could construct a bit mask, I could AND those fields together to pull off that one bit, and I could say branch if it's 0 somewhere, and that lets me, do something conditionally based on a single bit. But inevitably you'll encounter these, if not in this course, somewhere else, so I want you to see these. And they're classic features of reduced instruction set architectures like ARMS and PICs, because they're a tighter way to code branches. Fewer instructions and faster execution. Alright, all this stuff is in the text, by the way. If you look at the section on stacks, you'll see, pictures of drawing stacks in response to pushes and pops. You'll see lots of examples there. If you look at the section on branching, you'll see these skip instructions spelled out. So all of this is in the text also. But I wanted to mention it, and you've got some homework questions to work on. So work on these questions for Tuesday and bring questions Tuesday to class, because all this stuff is fair game for the midterm on Thursday. Okay, and your homework doesn't get turned in until next Thursday. So if you have questions, you got to bring them to class Tuesday instead of waiting for me to grade and turn back. Alright, so work on these over the next few days. Let's go on to the next topic. So the next topic is interrupts. And interrupts are a key to modern programming. They're a key to stateful programming. They're keys to making GUIs or graphical things in general. If you've done 223, we played with interrupts, but they were handled for us by Swing, and they were software interrupts. But it's a general concept. Okay, so here's the idea of an interrupt. Suppose you're waiting for a phone call from somebody. Right? I don't know. I don't use my phone anymore for calls, except my mom. My mom calls me. I answer. But nobody else calls me. So suppose you're waiting for a phone call, okay? And it's going to come sometime, between 10 o'clock and 2 o'clock while you're in class, okay? How do you handle this situation? There's two distinct ways of managing this. The first way is to keep checking your phone, right? Every 5 seconds, pull your phone out and see if there's a phone call. And if there's not, put it down, listen for a few seconds, and then take your phone, look at the screen again, see if there's a call coming in. Okay? That's an approach called polling. Polling is basically repeatedly checking something. We've done polling in code already. In Lab 2, if you implemented the code that waits for the inputs to change before going ahead and doing the addition and writing the output to port A, how did you do that check? You had a little loop that looked at port A, compared it to the last value, and if it was the same, went back to the top of the loop. That's a polling situation. That's continually checking. That's picking up your cell phone every few seconds to see if there's an incoming call. Okay? Obviously, that's an inefficient way to deal with your phone. Because if you had 100 things that you were waiting to have happen, right, you have to be doing these 100 things one after another, right? Is there someone at the door? So every 5 seconds you open the door to see if somebody's out there, right? Is there something burning in the kitchen? So every 5 seconds you stick your head in the kitchen to see if there's smoke, right? These are not the way that we live our life. Right? Because there'd be so many things that we needed to continually check, we'd never get anything done. And that's exactly what would happen on a computer. So what do? We have interrupts. Okay? You have a ringer or a vibrate on your phone, and when a phone call comes in, it makes a noise that gets your attention. And when that noise occurs, then you pick up your phone and you look at the screen and you see incoming phone call. And you go ahead and you answer it. Or we have a doorbell, and we don't check the front door every 5 seconds to see if someone's there, but when somebody shows up, they ring the doorbell, we hear that sound, now we go to the door and we open it to see if somebody's there. We have a smoke alarm in the kitchen, and when that starts making a sound, we know that there's smoke somewhere, so now we go and we check into the kitchen and we say, oh yeah, my food's burning. Okay? That's interrupt driven. So interrupts are an alternative to polling. And we basically let something grab our attention. No matter what we're doing, right? I can be asleep, and if my smoke alarm goes off, it's going to wake me up, it's going to get my attention, I'm going to respond to it. If it's a false alarm, you know, I'll wave a towel to clear out whatever made it go off, and I'll go back to sleep. But if there's a fire somewhere, right, I'll get dressed and go outside or whatever, right? So interrupts are a way to basically let something grab our attention. We have to set these up ahead of time. So we set up an alarm. We arm the system. We put our phone on, you know, we put the ringer up on our phone. We install a doorbell. We put batteries in the smoke alarm and hang it on the ceiling, right? So we set up the system, and then we can do whatever we want, and if some condition occurs and an alarm goes off, that grabs our attention. So I can be sitting here lecturing, you know, and if someone knocks on the door, I'll know that someone's there. And, you know, if I'm sitting here reading and someone knocks on the door, I'll probably get up and go see who's there. If I'm in the middle of a lecture and someone knocks on the door, I probably won't. Now, I might set a flag, right? I might put a note in my memory saying, oh, there's probably a package outside the door. And after I'm done with the lecture, I'll go to the door and I'll get my package, right? So there's different things that can interrupt us. There's different ways we may want to respond to interrupts, okay? All these things have analogs in microprocessors. Okay, so we can have priority levels. We can have things that we don't want to have interrupt us. Okay, for example, right now, if I get a phone call, I'm not going to pay attention to it, right? So my ringer is turned off. We may have priority levels. If I'm running out of the building because a smoke alarm went off and there's fire, and my phone rings on the way, I'm not going to stop to answer my phone. That's a lower priority event than getting out of the building in response to the smoke alarm. So we have priority levels. The PIC processor has 2 priority levels. Larger scale, more complex machines might have 31 priority levels. Okay, it's a feature of the architecture. But all of these systems have in common the fact that you need to set up the system, right? You need to control what's going to be able to get your attention and how high priority that event will be. And you need to turn on this whole system to begin with, because by default, interrupts aren't enabled on the PIC. Right? The things that can generate interrupts will not generate interrupts unless you do some work to say, I want interrupts to be allowed. Alright, so what are the key concepts here? There's different sources of interrupts. There's priority levels that we can set for most interrupts. Some of them are hardwired. Some interrupts are always high priority, but some of them we can set. There's source-specific settings. Certain sources have certain things we may want to tailor to say, you know, some other aspect of the interrupt behavior. we need to be able to enable interrupts. And there's two aspects to this. We can enable or disable each individual source of interrupts. And there's several things that can interrupt us. Actually, there's probably more like a dozen things that can interrupt us on the PIC processor. Changes to certain input pins, timing events, unusual conditions like stack overflows, arrival of serial data through some of the serial communication systems, completion of an analog to digital conversion, all sorts of things. So there's enabling or disabling interrupts per source, as well as enabling or disabling them globally. So I can say I want interrupts from the A to D subsystem and from the serial port and from pin such and such. But I also have to enable interrupts globally, right? And I can put on this giant do not disturb sign, and it doesn't matter if I've enabled individual sources of interrupts and those interrupts occur. I can globally say no interrupts, right, which is your default state. So we have to enable these things globally. And then interrupt flags, which let us tell once an interrupt has occurred what generated the interrupt. Because on a PIC processor, there's really only two interrupts. There's a high priority and a low priority. So we don't have a doorbell and a cell phone alarm and a smoke alarm and a window and a flashing light and all this other stuff. We basically just have interrupt, right? Or maybe interrupt, right? We have two levels of alert. And when we get that alert, we know something interrupted us, but we have to figure out what it was. If we've enabled 5 different things that could all generate an interrupt, we have to figure out which thing caused that interrupt. So there's flags associated with each possible interrupt. And then, how does the microprocessor respond to an interrupt? And this is something called an interrupt vector. And then we have to talk about side effects and more state-based programming. All right, that's kind of everything we're going to go over the next couple of days with respect to interrupts. But let me start, we got about 13 minutes here. Let me start with some of the basics here, looking at the data sheet. So all of this is controlled with special function registers, just like everything else on the PIC processor. Bunch of registers just like TRIS-A and Port B and ADCON1. There's a bunch of registers associated with interrupts. Okay, so here's our main interrupt configuration register. It's called INTCON. It has 8 bits, and with interrupts, you know, a lot of times the 8 bits in a register are going to do 8 totally different things. Okay, with TRIS-A, all 8 of the bits did the same basic thing. A 1 made a bit into an input, a 0 made a bit into an output. Now the bits affected different bits of port A, but they basically acted the same way. Not the case with the interrupt registers. Okay, so for example, bit 7 of INTCON, this is our global interrupt enable. This says, should we allow interrupts to happen? And in particular, ignore this GIE. Just look at GIEH. Global Interrupt Enable, high priority. So setting bit 7 to a 1 says that high priority interrupts are allowed. Setting bit 6 to a 1, that's our Global Interrupt Enable low, that says low priority interrupts are allowed. So those two are the main interrupt enable bits at a global level. High priority and low priority. Don't use GIE, don't use PEIE, even though you'll see these in some of the write-ups. Those are for a different version of this processor that we're not using, a different mode of it. Global Interrupt Enable high, Global Interrupt Enable low. And those symbols are set up in that include file. So if I use my bit set instruction and I want to turn on high priority interrupts, I can do something like this. Bit set file intcon, comma, global interrupt enable high, or global interrupt enable low. With interrupts, you want to avoid magic numbers. I could load binary 11000000 into W and move W into intcon, and that's going to be really unpleasant to try to debug. It's much cleaner to stick to these names like global interrupt enable high. When I see this in my code, I know, oh, I'm turning on high priority interrupts. Right? And in these pictures of registers, the word that you see in here, that's generally a word that's defined in the include file. All right, these 3 bits are used to enable interrupts. This enables interrupts from a timer called timer 0. This enables interrupts when port B changes value. RBIE says RB port change interrupt flag. We can set things up that will fire an interrupt when any of these pins on port B change, which is kind of nice. We don't have to poll. Okay, int0IE enables the interrupt 0 pin. And what's the interrupt 0 pin? Interrupt 0 is pin 8. So here's what I can do. I can set up tri-state B to make pin 8 an input. Right, make bit 0 of tri-state B a 1. And then if pin 8 gets 5 volts on it, that'll generate an interrupt. So I can hook a switch up and have that switch send a ground into pin 8. And as soon as I flip that switch and 5 volts appears on here, it'll trigger an interrupt. It's called interrupt 0. And if I've enabled interrupt 0 using this bit, and if I've enabled high priority interrupts using this bit, then when pin 8 rises to 5 volts, the system will interrupt. And when it interrupts, if I look at this bit in the register, I'll see a 1. So int0IF is the interrupt flag. If it's a 1, that tells me that the int0 external interrupt occurred. If I've set up interrupts on port B and an interrupt occurs, RB interrupt flag, RBIF, will be set to 1. So RBIF is equal to 1. At least one of those 4 bits in port B changed value. Alright, so incom lets us enable a few particular sources of interrupts. It also lets us enable interrupts globally. Intcon2 lets us do some customizing. For example, int0, I said that if it's 0 volts and it raises to 5 volts, it will generate an interrupt. Maybe I want a different condition. Maybe what I want is an interrupt when pin 8 falls from 5 volts to 0. In other words, on a falling edge. If I set this bit value to 0, int edge 0, that says generate an interrupt on the falling edge. So you can customize the behavior of some of these sources. Intcon2 sets priority levels. So int0 is always high priority, but int1, for example, I can set to be high or low priority. If I set this bit to a 1, it'll be high priority, 0 will be low priority. Defaults to a 1. And different sources, A to D conversion, serial communication, and so on and so forth, have different interrupts. There's one more register we care about, that's RCON. And before you do anything else with the interrupt subsystem, you want to set bit 8 of RCON to be a 1. That gives you priority levels. If you don't do that, all the high priority, low priority stuff is meaningless. Okay, it's compatibility mode with an older PIC processor. So first thing you want to do is set RCON bit 7 to be a 1. And then these are all status registers that you can look at to see things that have happened. Power outs, brownouts, and so on and so forth. Alright, so that's a brief intro to interrupts. We will dig a lot more into that Thursday. That'll be the main thing we're doing. Sorry, Tuesday. That'll be the main thing we're doing on Tuesday. But take a look at the problems and get some questions related to that. You can read more about this in the text. Had one question from someone. What are interrupts used for in high-level languages? For example, when you're writing a GUI, right, you might create a button and say, you know, when the person clicks on this button, I want you to run this code. That's basically done through a software interrupt. Hardware interrupts would be something like, you know, pressing a key on the keyboard instead of the operating system continually checking to see if a key has been pressed. The process of pressing a key changes the voltage level somewhere, and things have been set up in the OS so that generates an interrupt. Same thing, there's something monitoring the voltage, and if the voltage in the system drops below a certain level, that's a high priority condition. That's usually your highest priority interrupt, and it says, hey, voltage is dropping, let's synchronize our caches out to the hard drive and get ready for a possible shutdown. So these are used all over the place in operating systems. More so that than, say, a while loop. A while loop would really just be, you know, a branch, maybe with some kind of test condition and a conditional branch. But you don't necessarily need an interrupt for that. But anything that's interacting with outside hardware, with something that you know, can change state outside the system, that's probably a good place for an interrupt. All right, got you out of here 3.5 minutes early. I will hop into my office, chug away on the traffic intersection lab, and I will catch you later on. If I don't talk to you later today, have a good weekend.